everybody, and welcome to this tutorial. This is Clotilde Persson from Oregon State University, and today I will show you how to use Lark 2.0, which is a collaboration between Mirta Gaintatsi-Masuti from Eindhoven University of Technology and myself. And Lark 2.0 is actually an update to Lark Spectral lighting. So let's start from the Rhino 3D interface. As you can see, I have my 3D model, which is already drawn. This is a simple room where all the layers represent a different building material, as is typical for a lighting simulation. And I will directly call Grasshopper so that I can open it. And then in Grasshopper, I will open one of the 3 templates of Lark 2.0, which is the point-based simulation. So this template basically allows us to run point-in-time simulation of virtual sensor in the space, and it does not involve any image rendering. Let's zoom out of the template so that you can have an overview of what it means. The template, and each template actually in Lark 2.0 is divided into 4 parts. The first one is for the inputs to the simulation. The second one is where you can start to run the simulation. The third part is all the process of the simulation, and I will quickly go over each of these items later on. And then the last point is the outputs, where you can access the results of your spectral simulation. So let's start with the inputs. All the steps are actually detailed directly in the template, so you just need to follow what is written, but let's do it together so that I can show you. Here I can first decide whether I want to run a daylight simulation, an electric light simulation, or both. In this case I will do both so that I can show you everything. Then I need to define my virtual sensors. And in this case I can choose whether I want to have individual sensors, and these are linked to points that I can just draw in my 3D models and place everywhere I want in the 3D model, or whether I want to run for a sensor grid, in which case I will just draw a plane in my 3D model and I will put sensors on that plane. Let's do a sensor grid simulation in this case. So as I chose to do a sensor grid, I directly go to point 4, where I can select the plane or the surface. So set one surface, and this brings me to the Rhino 3D interface when I can directly select the surface that I want to simulate the sensor on. And I chose one that I had already drawn on the 3D model. I can then choose which sensor spacing I want the sensors to have, the sensor height, as well as the number of directions of all of these sensors. And just to give you an overview of where are my sensors, I can just preview here the sensor's location. So if I go to my Rhino interface, now I can see all the sensors are actually displayed in the interface. And they're indeed located on the plane. So the plane actually corresponds, it's actually here, to the surface of the room, 1.2 meter height and 0.5 meter in between. After setting up the sensors, I need to set up the daylight inputs. So here in the daylight inputs, first I will need to set up the time of the year and of the day when I want to simulate. Here it's set to 27th of May at 5 p.m. Then I can choose, I have the choice between 2 options. Either I can include weather file, an EPW weather file, and I will give you a link on the Energy Plus website where you can actually download this EPW weather file for all locations on Hertz. So I can just select one EPW file, and here I can actually access this weather file. Okay. So in this case, I set up the weather file in this box, but I could also decide to input myself the data that I want to simulate for. And so in this case, I would then toggle this component, and then I would input my data in this slider. Last part of the spectral sky definition is to define the SPD, which stands for spectral power distribution. By default, we use the D65 illuminant SPD, and these values are actually implemented here. So you can decide to do the simulation for another spectral power distribution of daylight, and you would need to change then these values in this case here. And then the second element here is just the wavelength resolution. So in this case we have wavelengths every 1 nanometers, which corresponds to the value of the D65 illuminant that we inputted in the first element. So we are all set up for the daylight light inputs. Now we need to input also the electric light inputs. What I need for the electric light inputs are the path to the spectral power distribution of that light inputs. In this case, I want to simulate a fluorescent lighting, and I already have the spectral power distribution of that fluorescent lighting in my data, and I can show you what it looks like. So it is just a text file where we have the wavelengths and then the value of the SPD. These data, you can actually either measure it and then run the simulation for something you already know or you measured, or you can also rely on some online databases, and I will put the link to one of these databases here so that you can look it up and find the one that you want. The second file that you need for the electric light inputs is an IES file. So this is a file that shows the light distribution. In this case, I will again take the one that I already have, and these files are typically provided by the light manufacturers directly. When you are inputting this IES file, make sure that in your template you actually also have. It is by default included in the point-based and image-based templates, but in case you are building your own templates, make sure that this component here is included. So basically, in this component here, the electric lighting one, there is a function IES2RAD, a radiance function, which if it detects the type of luminaire from the IES file, it will assign it a specific RGB color coordinates, which we don't know. We want these color coordinates to stay to 111 so that we can apply the rest of the workflow, the spectral simulation workflow for the electric lighting source, right? And so we need this to be 111 for that. So this first component, which is Honeybee one, does that and make sure that this default color stays to 111 even if IES2RAD detects the luminaire from the IES file. So just a quick note about that. Then I just need to set up the wavelengths interval in my SPD text file. I just open it, and if you remember, it was 1 nanometer, so I can leave it to 1. I can also set up a light loss factor, which is the ratio of how much light the real light source will output compared to the theoretical basis, which is set up in the IES file. So we typically use 0.8, but we could set it up to 1 so that we use the actual value that are implemented into the IES file. I can name the light source. I set up the Rhino layer ID of that luminaire, and I also use the layer filter in that component in the pipeline, so that so this component is actually picking up the geometry information into Rhino. And then at last I can also decide to rotate the luminaire in my 3D model, but I won't change these inputs now. So that's for the electric lighting. At last, before running the spectral simulation with Lark, are the materials. Two types of materials that we will use, either glass for the glazing, obviously, and one which will be used for the plastic, but basically it's all other opaque material that we can have in this 3D model. The first one here is, as you can see, from the pipeline or the geometry will be the window. So basically that means the glazing in this case. And so I will select the material type as 0. The spectral information of that material will need to be inputted here. And in the case of the glazing, it will be the spectral transmittance. And so I can select the file. For the spectral transmittance, we typically use a USR file, this one in this case. And this USR file, you can directly output them or create them through the Optics 6 software, which is a software free that is provided by LBNL. And I will also put the link here so that you can access this software. Then we set up the wavelength interval in this SPF USR file, and I can actually show you what this USR file looks like. So this is directly what Optics gives me, and so you have the wavelengths in the first column and then the spectral transmittance. So that's what we use for the glazing material. And then again, setting up the Rhino layer and then the pipeline to pick up the geometry. And we do that for all the materials, and so I will quickly change, in this case, all the spectral reflectance of these materials. So here I was dealing with the walls, and so I have the spectral power distribution of the walls. So these are spectral reflectance of these materials. Again, you can use values that you already measured. If you don't have any measurements, you can also look up on this online database, where you also have free access of measured spectral reflectance. So I will include that here, and I will show you what the format of this spectral reflectance looks like. And so in this case, you have again the wavelengths in the first column, and then the spectral reflectance value. And here we can see that we have the data only for every 10 nanometers. Okay, so I have set up, in this case, my walls, 10 nanometers interval, the Rhino layer, the pipeline is correct, and then the material type, in this case, I set it up to plastic. And I will do that also for the floor here. And for the ceiling here. And at last, I also have the facade, which in this case, I set it up as the same material as the wall here. Last but not least are the simulation parameters. So these are the Radiance simulation parameters. And so if you don't know how to set them up or what they mean, because I won't go into details here, You can just refer either to the Radiance forum or also to the Radiance book where you can read how to set up these parameters. But in this case, I want my simulation to be relatively quick, and so I will lower down these parameters so that it goes faster. This last one is actually just the two components that ensures that honeybee and ladybugs, which are used to run the simulation, are well loaded into the template. So the next step, once all these inputs have been set up, you can see that at least here in the first part, we don't have any red elements remaining besides this one. And the reason why this one is still red, which means that there is an error, is because we still need to create the light source file. And so this we will see here. So to run the simulations, there are actually two steps, where the first one is to create the spectral electric light source files and the spectral sky file. And so the spectral sky file is actually the file that we'll need for this component. So you will see that as soon as I will turn it to true, it runs, it goes quite quickly to run, and then you can see that there is no error anymore because it created the spectral file that this component needs. So we have created these light source files, and now we can actually launch the simulation. And I will do that now. And while the simulation runs, I will actually show you the process. And so when you run the simulation, you will have these terminal windows that will appear, and this just means that the Radiance simulation is ongoing. Okay, so if we look at the process, what we can see is actually, let me zoom out. This first part of the process, you can see that there are two parts in the process. There is this first column and then that column. The first column is actually where all the inputs are processed so that they can be used in the spectral simulation, and this second part is where the actual simulations are run. In Lark, we actually do spectral simulations in 9 channels. So that means that we run 3 Radiance simulation, three channels simulations. And so we have the blue channel simulations up here, the green channel simulations there, and then the red channel simulations, right? And so for all these simulations, we all have to create the blue inputs, the green inputs, and then the red inputs. So if you click there, you can actually see that the green is linked to the green simulation, the red is linked to the red, the green is linked to the green, and then the blue goes to the blue. And so all this first part is just to process the inputs that we give to Lark into these blue, green, and red inputs. So for the spectral sky, what it does is it reads either the EPW file that we have given, or it reads directly the component to create the spectral sky model. So this first component here is actually one of the original components from Lark, where it reads spectral information and it outputs it into 9 channels. This one is also part of the original Lark spectral lighting tool, but it was updated to run a new sky model command, which is gendelete in this case. And actually, if you double click it, you also have access to the code. And in that code, you can also see, well, obviously the copyright, but all the updates that have been made to that component since it was first released. Then after the spectral sky definition, we also have the spectral electric light source definition, where we also use the same component to read the spectral information from the electric light and output it into 9 channels. We have the view sensors definition, nothing much going on there. And then for each materials, we also use that same original Lark component, which will read the spectral information. So that's for the pre-processing of the inputs. Then each of these section will actually run one simulation, as I mentioned earlier. In this case, we run the blue channel simulation. So that is a typical Radiance Honeybee simulation setup. So that is actually the component that runs the simulations. And then once this is done, we end up with the outputs in this section of the screen. And I will zoom in so that you can see again a bit more. So we have 3 main outputs or 3 sections of outputs that we provide in Lark 2.0 or in this in Lark 2.0 in this template. The first one is using the original component from Lark, where we can output directly the photopic lux, but also the circadian illuminance according to Lucas et al. Melanopic curve. So that's one, which gives you the values for each sensor point, right? So you can scroll down and you have all the values. We also provide alpha opic quantities. And so basically we implemented the CIE toolbox as a component of Lark 2.0. So the CIE toolbox is for the alpha opic framework that was developed by the CIE. And so you can, based on the outputs of the simulation, the 9 channel outputs, you can choose which alpha opic curve you want to calculate. In this case, we selected the melanopic one, but you could select either of those. And then it will calculate the alpha, or in this case, the melanopic irradiance, the melanopic ELR, and the melanopic EDI. And these values are displayed in these boxes for all the sensors. A last output from this element is the spectral irradiance, which is displayed here for all the sensors. As it is only a 9-channel simulation, we will have a step function representing the irradiance with the 9 channels. And so you can actually count these, there are 9 of them. And these outputs are also written into a CSV file that is directly outputted in your Lark working folder. So in my case, I put it here in the quick access, but you can directly access it at the root of your Windows machine. And you can see that this file has been written here. And so you have the spectral irradiance, which is outputted into that file for each point. And so here you can see that you have the coordinates of the point and then the view direction vector, and then the spectral irradiance, which is written there. And then the last output that we wanted to provide you in this template is actually not directly displayed in this template, but is directly displayed in the Rhino viewport. And so you can actually look by yourself at the result in Rhino. In this case, we cannot see much because the arrows are a little bit big, and so I will make them smaller so I can, R0 is a bit too small. I can reduce the size and then I can zoom in, and so you can see for each sensors the 4 view directions, and then what is displayed here is the melanopic EDI, and you have the scale that is displayed here, but you can see here melanopic EDI in lux value. You have also the information about the simulation that you just ran. So in this case, we included both daylight and electric light on 27th of May at 6 p.m. And so if it's still too crowded, we can also remove the values. And so I can just remove the preview here. And so here we have this nice display of the output of the simulation, and we can see that the sensor facing the window provide actually the highest melanopic EDI. And with that, I am done with this tutorial for the point-based simulation. Thank you for listening, and I wish you very successful simulations.